So today we're going to start learning how to actually solve polynomials by factoring. Yesterday we graphed them and we got decimals, but now we're going to look at integer answers when we are factoring. So a polynomial that cannot be written as a product of two polynomials with integral coefficients is called a prime polynomial. Like a prime real number, the only factors of a prime polynomial are one in itself. So sometimes you're going to have polynomials that don't factor. But when you do have polynomials that factor, they're going to fall into one of these cases. If you have any number of terms in a polynomial, you should always check for a greatest common factor. This is always the case. We'll see one example like this today in our notes. Then, as a reminder, also remember we have this rule about the difference of two squares. That was back from like when we were factoring quadratics. For example, if I gave you the quadratic x squared minus 4, x squared and 4 are both perfect squares. So we know that this factored as x plus 2 and x minus 2. And that was a difference of squares. So today what we're going to focus on are these two here, the sum of two cubes and the difference of two cubes. Tomorrow we'll look at, if you have 4 terms down here, we'll look at grouping, but that'll be for tomorrow. So the sum and difference of cubes are just formulas that we're going to be applying. If it's a sum of cubes, notice there's an addition here because that's a sum. And so it falls into this general case where you'll have a plus b times a squared minus ab plus b squared. So you'll find a term a and you'll find a term b, and then you just kind of plug these in. You find those a's and b's by taking the cube root of the original two terms, and that's what your a and b will be that you're going to plug in. The difference of two cubes is where you're subtracting them, and so your first factor will have a minus, and then the other factors have a plus. So notice there is always one minus in these factored forms then, but for the sum it comes second, and for the difference it comes first. So example 1 just wants us to factor each polynomial. If the polynomial cannot be factored, write prime. So as we look at this part A, and you don't have to write this, I'm going to write the formula every time just so it's on the screen for you. You don't have to write it every time, but this is x cubed plus 64. So this is going to be a sum of cubes. And the sum of cubes is the formula a cubed plus b cubed will factor to be a plus b times a squared minus ab plus b squared. So my first task is just to find my a and b. So I can do that by taking a cube root here and a cube root there. So my a, the cube root of x to the third, would just be x. And the cube root of 64 is my b, and that would be 4. So then I just have to plug those in here into this general form, this factored form. So when I do that, it will end up being x plus 4 times, and then it's my x squared, my a squared, x squared, minus x times 4, which we don't normally write it in that order. I'm going to fix that in a second, plus 4 squared, my b squared. So I just need to simplify. So it'd be x plus 4 times x squared minus 4x plus 16. Now we're going to see in this section that anytime you have a square still in one of your polynomials, a square above, you should continue to factor if you can. But what you're going to find is that for the sum and difference of cubes, they will never factor further. This will always be your final answer. And in fact, just for this one, I want to actually check the answer just so you guys see that this does actually work. So if I were to FOIL this back out, I should get back to that original. So let's look at our check here. If I were to multiply out x plus 4 times x squared minus 4x plus 16, if I multiplied this out first, I would have x to the third minus 4x squared plus 16x. And then if I multiplied in the 4, I would have plus 4x squared minus 16x plus 64. And so you can see that this minus 4x squared cancels with positive 4x squared. The plus 16x cancels with the negative 16x. And you're back to that original x cubed plus 64. So that's why we know that we did factor correctly here. Just move this over so we can get into our next problem. So we don't have to check again, but I just wanted to show you why that works. All right, part B, we have 27m to the third minus 8. It's again helpful if you know your perfect cubes because you can hopefully see what these will be right away. But this is going to be a difference of cubes. So again, I'm going to write the formula just so it's right on our notes on our screen, but you don't need to write it as you're doing your notes because it should be up on the board for you. But this is the case where it's a cubed minus b cubed. So it'll factor as a minus b times a squared plus ab plus b squared. So I just need to find my a and b and plug those in. So I'll take a cube root here, a cube root here. So my a term would be 3m, and my b term is 2. So now I have an a that has two parts to it, so I have to be a little more careful when I do my substitution. So my substitution will be 3m, my a, minus my b, which is 2. It's this first part here. And then the second part, here I'm going to have to add parentheses because I do need to be careful. It's a squared, which means it's all of 3m squared, not just 3m squared where the square is only on the m, plus 3m times 2 plus 2 squared. So when I simplify here, this second parenthesis needs some cleaning up. This square goes to both parts here. So I'll have, I have 3m minus 2 times 3 squared is 9m squared plus 3 times 2 is 6 plus 4. And that's my final answer. So the cleanup took a little more effort. So you just really need to watch. If you have two terms here, make sure you put a parenthesis or know that you're going to square both of those. So it's not just 3m squared. It really is 3 squared m squared. Anytime you have two terms, you have to apply that to both. Let's look at two more. These get steadily harder. So now part C, we're going to have two terms for both our A and our B. Again, I'm going to write the formula right above it just so it's on the screen. This is an addition sign here, so we are in the sum of cubes case. So it would be a cubed plus b cubed will factor to be a plus b times a squared minus ab plus b squared. So I look at my first term for my a. If I took the cube root of 8x squared, my a would be 2x. If I took the cube root of 125y to the third, my number part of the cube root of 125 is 5. But then just as a reminder, the cube root of y to the 12, it's like you just do 12 divided by 3 divided by your root there. So it's going to be y to the fourth. Once I have that, I'm good to plug in, and I have to carefully plug in because there's two terms for each of these. So the first parenthesis is pretty straightforward. It's going to be 2x plus 5y to the fourth. Nothing to clean up there. But then my second parenthesis, I want to add some extra parentheses just so I know how the square works. So it's all of my a squared. So it's 2x squared minus 2x times 5y to the fourth plus 5y to the fourth squared. So I have to carefully add in that power here and there and there and there. So rewriting this, it would be 2x plus 5y to the fourth. And then my next part would be 4x squared, because that's that 2 squared, x squared, minus 2 times 5 is 10, y to the fourth, plus 5 squared would be 25. And then y to the fourth raised to the second. Remember, our exponent rule says that when you raise a power to a power, you actually multiply those exponents. So it should be y to the 8th. And that's my final answer for part C. Again, as a reminder, you'll get these kind of ugly second parts, that second parenthesis. Normally we would try and take that further and see if it could factor, but these will never factor further when they're a sum or difference of cubes. Okay, last one. And this is where, again, it's really helpful if you know your perfect cubes. If you do know your perfect cubes, you should recognize that 54 and 128 are not perfect cubes. However, again, looking back at this chart that we're going to use to kind of generalize what we should do with any polynomial, what methods to use to factor it, we are in the case where we do have two terms, right? So we're in this second row right here, but it's not a difference of squares, but it doesn't look like a sum of two cubes or a difference of two cubes. But don't forget that we always want to check for a greatest common factor. So here, 54 x to the 5th and 128 x squared y to the 3rd. Coefficient-wise, these are both even numbers, so we know they're both divisible by 2. And then, in fact, they both have a power of x, so we can actually pull out an x to the 2nd, because that's the biggest x that they both have. Now, we don't want to completely lose that. Make sure you write it down, because this is not set equal to 0. We can't just make it totally disappear. So we need to leave it in the equation. But then we will have 27 x to the 3rd minus 64 y to the 3rd. And so now this part in black really is a difference of cubes. So again, I'm going to write the general formula. Don't feel like you need to do that. So it would be a cubed minus b cubed, which will factor as a minus b times a squared plus ab plus b squared. So as I look here, and I'm going to do some green just so I don't get confused, the cube root of this part is going to be my a. So a here would be 3x. And the cube root here is my b, and that would be 4y. I know it's also tempting to like do negative 4y because of that negative sign there. You don't have to do that because this general formula takes care of that already. So kind of just ignore the sign there. So then when I go to plug this in again, I'm going to have to use parentheses, and don't forget that initial 2x squared. And so I'll have 3x minus 4y times my a squared. So it will be 3x squared plus 3x times 4y plus 4y all squared. Going to go ahead and distribute in that square power to both parts. I still have the 2x squared hanging out front. I have then the 3x minus 4y times 3 squared is 9x squared plus 3 times 4 is 12xy plus 4 squared is 16y squared. So it looks ugly, but really this is just plugging in an a and a b, being careful with our powers and our coefficients, but it's not too crazy. So that's completing, or I'm sorry, not completing the square, sum and difference of cubes. Tomorrow we will look at factoring by grouping, where we have more than just two terms.